Ciao, Frederick. Cedric, maybe. What is the correct pronunciation of our name? Cedric?
I'm French, so the pronunciation is Cedric.
Cedric.
But
okay.
if you want to pronounce it in English, it's Cedric.
Oh, thank you.
It's an English name.
Okay, understood. So an English name. You're born in France, and you're working in Spain. International.
Yeah, I'm not even born in France.
Okay.
I guess if you want to pronounce it the Italian way, it would be Cedric, Cedrice, o algo así.
Cedric, in Italian, simply. Okay, let's wait another couple of minutes. Okay. So, did you try to do the exercise, or did you eat? Oh, fantastic. Very good. Okay, now let's wait until another 3 minutes, and then I will show you the solution, and we will pass another argument. So, okay, let's recap a minimum. The exercise is to formulate, to include in our cube problem, also this kind of constraint that is an inequality constraint. We show how to transform an inequality constraint into an equality constraint by adding some Gauss qubit that we can use to make our calculations. Okay, so we show that the constraint total number of antennas less or equal than f is equivalent to ask the total number of antennas plus f Gauss qubits has to be, this sum has to be equal to f. Then we do the math, and then this is I want to record you that the same math that we show exactly here. You have only to replace n with n plus f. Okay. And then you can encode it into our QUBO problem. So what is the way to properly include it? So now we have another number of qubits, that is this n tot. The n tot number of qubits is NA, that is f, the additional Gauss qubits, and the 20 original qubits. So the first thing that we have to do is to consider all our variables as vector composed by n tot variables. Okay, because now the entire calculation has to be done over this extended set of qubits. So the right way is this one. You have to define your variables, including the Gauss qubits. It's important to initialize these variables to 0. In this way, we can use these zeros to not interact, to avoid the interaction between Gauss qubits and real qubits. Okay, because we know that for this formula here, the beta 1 minus 2f and 2 beta factors only has to act over the f qubits. All the other constraint and QUBO formulation parts must not interact with the Gauss qubits. Okay, so we make this one. You make this replacement, but when I create the radius, in this case, when I calculate the radius of every antenna, I have to do this only over the first n qubits. Okay, so in this way, with the same philosophy, this I can do this without tot. So also in this case, we have n tot areas, but only the first n are filled with values different from 0. Okay, let's run every cell in order to see if everything is good. Yes. So now we have to continue replacing this with this, and of course this with only the m. Is clear to everybody why I'm doing that? So noise here, and here only the n. Okay, now it was my cat. I don't know if you heard it. Okay, now we are here. Q the array. How many qubits we have? N tot. So the same thing, we have to do this. Also here, it's important to do the entire calculation over all the qubits, because in this way we can be sure that the constraint, the inequality constraint, will act only on the Gauss qubits, because we can write here the same things that we brought here. Okay, so this one, and this one. With this is without. Oh no, let's take this other one that is more complete. This one, yes. Oh, is this one? Yes. Put in here. Took this other one, and I put it here. So why I'm sure that only the constraint is acting on the Gauss qubits, because here I'm cycling over the total number of qubits. This case, I know that L is different from 0 only in the only over the indices that we want to keep. But don't worry, because in this case we have gamma equal to 0, so this is 0 always. But if we want to make a try using gamma equal 1, we can, because we are sure that the L value for the Gauss qubits is 0. Also here, because area with I is is different from 0 only on the qubits that are part of the original problem, because we brought here that area is filled only for the first n qubits. So I'm sure that when I'm looking for the Gauss qubits, it will be always 0. The only thing that will be not 0 is this one, because here I have no zeros, no way to say to the problem, don't evaluate this part if we are in a Gauss qubit. But it is right, because we want to evaluate this part for the Gauss qubit. Same thing here, same philosophy, I have nothing to make it 0. And for this part, I'm sure, because of from the same thing that we did with the area, also with noise, we can be sure that this value is different from 0 only for the first n qubits, the first n couples in this case, n squared couples. Okay, so I can do this. Also here, I have to loop over all the qubits, this one, and then let me see if everything is good. Seems to be. Okay, now I'm trying to solve in this with a little bit number of trials, only because I want to show you with this. Yes, I have this print. So I requested, where is the F value? This time the F value is here only because I need it at the beginning of my problem. F is 4, so I requested less or number of antennas less or equal 4. If we look at all the solutions here that I found, here I'm looking for all the decoded samples, not only for the best sample. For all the decoded samples, I can print the sum of the solution. The sum of the solution is number of the because this part of the solution is only for the first n antennas. So now I'm forgetting about the Gauss qubits. And in this way, I can say that I can print the sum of the solution. That is the number of antennas that are used. And you can see here that the number, we have 50, is always less than 4. Okay, less or equal 4. So constraint has worked. We see here the solution with 4 antennas. The complete, Cool. The complete graph, and then our solution estimation here, our analysis. Okay? This is the way to implement a inequality constraint. Now, let's move on to another. Okay, sorry, problem with the computer. Okay, now it's good. Okay, now, suppose we want to add another inequality constraint to our problem. This time, without much surprise, we will see the other sense of the inequality symbol. So, let AM be a measure of an area.
Sorry.
Yes.
Daniele,
Yes.
The shape of the Q array is augmented by n by number NA, right? By F.
Yes.
The shape is bigger.
Yes, of course. But when you decode your solution, you will look only at the first qubits. So in this case, we have the best sample that is running over the 24 qubits, 20 qubits for the original problem, plus 4 qubits that you asked here,
right,
for the ghost qubits. But when you extract your solution, you have to consider only the first 20 qubits.
Yeah. Okay, thanks. Yep.
Okay. So, the problem now is turn on the antennas so that the minimum covered area is greater than or equal to AN. Greater or equal than AN, sorry. So, this is mathematically our problem. We want that the sum of all the covered area has to be greater or equal than a fixed value. Okay, so how we can transform this inequality into an equality with the same thinking about the other inequality constraint. Now I will take another set of qubits. This time I will take n qubits because it is very, very a personal choice, because in this part, when you transform an inequality to an inequality constraint to an equality constraint, you have always to make boundaries. Okay, so in this case I can approximate, because of course this is not a real equivalence, because this number can be with this kind of equation, this equation will be, it can be very, very large, no? But in this case, I'm saying that my, for example, yes, this is also impossible everything on, but a way to see, but we do better, but a way to see this inequality constraint may be to add to this minimum value the sum of other fake antennas with their areas. Okay, so I'm saying that the area covered by the surface covered by all the antennas that will be activated during the solution of the problem has to be equal to a minimum value AM plus some positive value, or also 0, okay? And it has to be a variable, so I will take another n qubits, n ghost qubits, and I will associate it with the corresponding areas of their real qubits. Okay, so I duplicate my qubits and duplicate my areas. Here, mathematically speaking, I can bring the second summation to the first term of our equation. And how can I merge these two terms? Because in the first inequality constraint, we had a plus sign, so it was really easy because it was the same thing, but you have only to enlarge the summation. Okay, this time, oh, sorry, this is an error. It has to be a k here, of course. Sorry, I'm seeing only now. Okay, so we have to merge these two summation. How can I do? Maybe one thing, maybe this one. What is the CI that I added? CI is simply a vector that has +1 values when I is less than n, and -1 symbol when I is greater than n and less than 2n. Okay, for the first set of qubits, CI is +1. For the second set of qubits, CI is -1. This allows me to write this summation into a unique summation. Okay, of course, it's not the only way to do this kind of stuff, but it's a way. So let's do some math. We have this condition here. We have to see it as a minimization problem in this way. And then we have to develop our square. So this is the square of the first term. Here it is. The double product of this term and this term. Here it is. And the square of the AM term that I can throw away. So I have to develop this other square here. And I have the square of the first member. So what is the square of the first member? The square of the first member, the part inside the summation. The square of the part, the sum of the squares here is c squared, but if you remember the definition of c squared, it's only composed by +1 and -1. So its square is 1, always. So I can not write it in the summation. A squared, that is a square, because it's an area and we have no shortcut in this occasion. And the qi squared, that is qi, plus the double products of the elements inside the summation. So we have this double summation here, 2 times what? Ci, Cj, Ai, Aj, Qi, Qj. I also forgot a Qj here, sorry. Okay, so minus this other term that remains the same. So what we have here? The first term and the last term are linear terms for my equation. So I can sum it up and I obtain this coefficient here. A squared with I, AM, Ci, AI. Yes, we have it, is correct. The other one remains the same with Qj at the end, of course. And it is the quadratic contribution to the problem. So let's try to implement this one. For this one, it's a little bit more difficult, but it has the same philosophy of the last one. This is this one, constraint greater than AM. Okay. So what we have to do? First of all, we have to create the C vector. Okay. Let's do this together. I will let you, I don't know, 5 minutes or something like that to see something here, to have an idea. What we have to do, we have to create the loop for C C vector. Okay. So I was saying, we were here, sorry. Okay, we have to write the loop to create the C vector. So remember, C vector is a vector that has +1 for the first n qubits and -1 for the last n qubits. So here we have to replace with the right dimensions. Also here we have to add another thing, because differently from the last inequality that we saw before, this time I have also areas for fake qubits. Okay, so I need to copy the areas of the real qubits for ghost qubits. Okay, so try to solve this cell here, 2 or 3 minutes, and then I will solve it with you, and then we go together. So, did you make it? Okay. So, I will show you the solution because I want also to show you some other examples before the end of the lesson. So now this part is pretty simple because I have only to make a, for example, something like that. See, of course, there is a lot of ways to do this kind of stuff, and maybe better than this one. But one way to do this can be this way here. Fantastic. Yes, of course. This is another way to do this. I will. Oh, what's happened? Okay, I will do. We'll copy your solution. Good solution. Thank you. Okay, so now I have my vector here. So let's do the same thing that we did before. Of course, this is all the dimension has to be n dot, and all the loops has to go only for the real qubits. Okay, so this and so this. In this, we can do something like, for example, this area. Okay, I can do something like that. Okay. And then you can say that area with I has to be equal to area I minus n. Okay, so in this way, I copied the areas of the first n qubits that I calculated with this loop on the fake qubits. So this way, also the fake qubits as areas. This is an error. Because yes, of course, we have to run it from the beginning. And this is our result. So here, same thing. We have only to replace the dimensions. This time there's no need to copy also the interference on the fake qubits, because our constraint does not involve also noise for antennas, only the areas. So this and this. Okay. This is ready. Perfect. So now, of course, I will replace it with the n dot. The shape is here is n dot, of course. This is n dot. This is n dot. Okay, now looking at the slides and considering the mathematics behind our new constraint, try to implement it in a correct way, replacing the values for A and B. Remember, the first part, of course, can be, because now I want to activate all the constraint that I have. So we have to repeat the constraint that I had before. But I have to make some attention here, because something has to be restricted. Okay. Let's take 5 minutes to think about it. So remember that the mathematics that you have to implement is this one. precisely this one here, linear part and quadratic part. Now remember that the F constraint that is turned off, but the F constraint here is an equality constraint, okay? So I decided to not to mix the inequality constraint. So remember that here the constraint regarding F is an equality constraint, okay? Another couple of minutes. Are you trying? I don't know, maybe with this high temperature. Gauss for how to initialize them. Okay, lossless loop of the Gauss qubits for cell. What loop? What loop? 1, 2, 3, 4. Here. For the Gauss qubits, what is the loop for the Gauss qubits that we're talking about here? Because here I'm not defining qubits. I'm only saying to the problem that I have 14 qubits. Okay, I created the C vector. In this case, has to be an A to be precise. To be a vector. Okay, this one did the area because every fake qubit in our problem now has to be connected with an area, because now in this here we have the area of AOI that is connected with the qubit that acting also on the ghost qubits. Okay, so this time, differently from the last session with I have to also to consider the fact that a ghost qubit has to have an area. Okay, it's saying here because it's simply appearing. So to do that, I cannot put like the other time my area to 0, but I have to copy, and I cannot create some other areas, but I have to copy the area that I calculated for the first 10 qubits to the last 10 qubits. Is more clear now? Perfect. So let's see what is the mathematical form of this problem here. So first thing that we want to add is, of course, this one. So, of course, I can put my constraint, my L constraint here, because I'm sure that it will not act on the ghost qubit, also because L is a vector composed by zeros. Okay, so in this case, gamma is also 0, but thinking in general, this is what I have to do. Then I add areas. Okay. Then I add beta. Then I add the mathematical constraint. Mathematical constraint of this new constraint. That is this one. Okay. So now the parameter that I'm using to regulate this constraint is called delta. The minimum area is 1.3, and following what I obtained here for the linear part, I will add this part here, and this is the result. We have delta A squared minus 2 delta CIAM A. Okay, seems to be good, but it's not. Why is not? Because we always have to care about the fact that fake qubits cannot interact with other parts of the QUBO problem that are not related to their constraint. So in this case, I said that with L, I'm sure, because L is 0 when the qubit is not, in particular, L is 0 when the qubit is not in the first 10 qubits. But this time, for example, area with I is a problem. Why is a problem? Because in the last constraint, I said that area was 0 if I was greater than n. Okay. Now, for my constraint reason, I had to fill also the areas of the fake qubits. In this way, if I leave it in this way, I am maximizing also the area of the fake qubits, and this is not good. Okay, this is not what I want. I want only to maximize area for the real qubits, not to maximize area for the fake qubits. So one stupid thing that I can do to avoid this problem is this one. Multiplying this value for this function, really stupid function that I wrote at the beginning of this code, that tells me if I is less than m, return 1, else return 0. So I'm sure that I will, in this way, I will turn off the maximization of area if the area is not belonging to a real qubit. Okay? Same thing that I have to do is this one. Also here I have to add this part. Why? Because in the last exercise, this part of the constraint was applied also on the fake qubits for reason of for mathematical reasons, because the constraint said that it has to be applied also on the fake qubits. But this time I'm applying the equality constraint. So now this constraint has to be applied, to apply only to the first n qubits. There is no sign of this part inside the new constraint, the inequality constraint. Okay, the only thing that has to act over the real qubits and fake qubits is this part here. This part of the constraint. Okay, is it clear?
Just a quick question here.
Yes.
Wouldn't it be the same by creating or using the C vector or creating another vector that takes value 0 or 1, depending on fake or not fake?
Yes. This can be also another solution. Yes.
Okay.
Yes. Yes. It's the same thing that if you think about it, this function is this vector that you're talking about. Yes. Okay. So for the same reason, I can write the quadratic part in this way. So alpha star noise ij. Here I can not use the function to guess if the qubit is fake or real, because I know that noise in this case, like the other case, the other inequality case, is different than 0 only for the first n qubits. Okay, so this time here I'm okay. I don't want to do anything. This part here, to the star beta, needs to be rewritten, and this time I have to use this function 2 times, because I want that this part is true only if both of the okay, yeah, only one little thing that I see, but this is the same, e plus 1. Okay, so I'm saying it's the same because here is written in this way, and it will use only this one, but it's more precise here. I want this quantity to act only if both qubits are real. Okay, so doing that is the same to call this function 2 times. It's 1 only if both are 1. Okay, plus 2 delta ci cj area I area j, that is the part that came out from our constraint. So this is the form of our this is the shape of our QUBO problem. Let's see if it's good. Okay. So I'm saying that the minimum area has to be 1.3. And we obtained an area of 2.0. It is greater than 8.3. Also, if I want to consider the sorry, a moment, I'm at home, so my phone is ringing. Sorry. Okay, sorry for the interruption. Okay, here I am. So I was saying that we can raise this number here. Okay, so I'm saying to the Cubo problem that the minimization of the interference is very, very important. Is more important than before, because before it was set at 0.3. Let's see what's happening. This time I've obtained an area that is 1.29. That is because now problem is trying to maximize the area, minimizing a lot, taking into account the fact that he has to minimize the interference. So it's trying to find a way to obtain an area that is close enough to our constraint, but with the minimum interference possible. For example, we can see here this other solution obtained this number of times. We have a solution here that has the solution chosen that has an area of 1.29 and an interference of 0.05. The other area that is slightly bigger, 1.3, has an interference that is more than double. So the program chooses to use this other one because as in ratio, the interference is much lower. Okay, understand the situation? Perfect. So
can you show us the solution again for AI and BIJ?
The solution for, sorry?
AI and BIJ, the two.
Yes, the solution or the implementation. Of course. This evening I will upload all the solution of the on the repository. So.
Okay. Yeah.
Remember tomorrow morning when you wanted to update the repository, you will find also solution.
Okay. Thanks.
Okay. You're welcome. Perfect. So let's move on.
Jesus Christ.
Okay, now it's something that I want only to show you. It's nothing real difficult. And this is a feature of PyCube that we can use without a problem. We say that sometimes it's necessary to add some terms of order 3 or higher to our problem. Okay, so what we can do if we have something like that? How can we relate to a Cubo problem? It's possible to transform a multiplication with 3 qubits into a multiplication that involves only quadratic terms. This equivalence can turn this multiplication here into this sum of multiplications that includes only the only quadratic terms and a new qubit that can be used to calculate these values here. You can see in this table that the values of these two forms are identical. Okay, so how we can use it in our program? Very, very easily. Let me see if there is something here. Okay, this is not an exercise. You have only to look. It's very, very simple. So here we are. We are creating the array, we are doing what we have to do, we are adding our terms to AI and BJ. So now let's think about the fact that we want to act also this other constraint here. So these are order 3 constraints that are saying that the contemporary presence of antennas 1, 2, 3, antennas 1, 4, 0, and antennas 5, 7, 18 are penalized some way. Okay, so if they are present all three together, we will add a certain quantity to our problem in order to penalize this combination here. And this is done. Okay, you have to do nothing. You have not to transform these terms into quadratic terms with your hands, but you can use PyCubo features that allows you to do that. Okay, this is the only thing that you have to do. You can always, of course, write it by hand, but it's not necessary. Okay, so let's see. I want to show you that the solution for the problem of the simulated annealing sampler has some strange qubit. If you see here, we have Q15, Q1, these are normal qubits. At a certain point, we have this qubit here, named 3 star 6, another qubit 3 star 4, another qubit 0 star 1. Okay. This is ancilla qubits. These qubits here are the W qubits that you see here. These W qubits here, okay, that are used to implement also this kind of constraint. Okay, is it clear? Very, very easy. You have only to do that, and this is the same for every. That's the same as before. Okay, so let me show you another thing. Oh, okay. Now, speaking about graphs and embedding. So, mathematically speaking, we know that an undirected graph is defined as a set of vertices and edges. Okay, vertices, you know that these vertices or nodes are the center of other points in the graph that are connected with edges that are a subset of v times b. Okay. So each node and each edge can be weighted with an arbitrary value. In this way, it's possible to establish a one-to-one correspondence between a weighted graph and a Kubo function. Okay, so every Kubo function can be easily transformed into a graph, a weighted graph. Example, this very short Kubo problem can be written as a graph in this way. Do you agree with that? I hope yes. So, but what if the graph that we wish, so this is a way to write our Kubo problem inside a graph. Okay, so quantum annealer is something like that. Okay, is a graph. It's a graph composed by qubits and edges that are connection between qubits. And then solving a Kubo problem on a D wave is equivalent to solve a Kubo to transform our Kubo problem into a graph. But the D wave graph is not an arbitrary graph. Okay, is a graph that has a topology fixed. So what if the graph in which we want to represent the Kubo function does not have enough vertices or edges to do so? Of course, if there is not enough vertices, there's nothing to do. You cannot map your Kubo problem into a graph that are less qubits than your variables. But if the problem is edges, it's possible to do. How? So we can observe in the figure the chimera graph. This is the topology of one of the D-wave models, the penultimate one. Okay. because the other topology is Pegasus topology is more complicated. We will see it. But now, as title of example, this is better. Okay, so we have to map our QUBO problem into the graph of our quantum annealer. This procedure is called embedding. So when you hear embedding a problem on the D-Wave system, means create a QUBO problem, transform your QUBO problem into a problem that fits with the topology of the wave. So suppose we have a QUBO problem that can be translated with the following graph. Okay, we have 3 nodes, 3 qubits, so three what you want, 3 binary variables with weights and 3 edges with weights. Suppose that we have a quantum annealer with a graph of this shape. Okay, we have a mini annealer with only 4 nodes and 4 couplers, and we want to solve this problem, the triangle problem, using this squared D-wave, the square annealer graph. It seems impossible, but it's not. One way is to force some qubit acting like one. This is the reason that I show you when I used the real quantum annealer. This is the reason why some qubit has to be represented, some variable or logical qubit. A logical qubit is always a binary variable that exists only on paper. Some logical qubit has to be translated into different qubits. Okay, so this is the case when I'm using only 2 qubits, but we will see that sometimes we have to use a lot more qubits. Okay, so the qubits in this representation, qubits are forced to act together, and we can say that is a sort of entanglement between these 2 qubits. Okay, they cannot, if measured, they cannot be discordant values. Every qubit involved in the same chain, it's called the chain of qubits, has to be entangled. So every qubit has to have 1 or 0 value, not mixed values in the same chain. Okay, this is an example of the chimera graph, and this is an example of the Pegasus graph, the last one, 5,400 qubits a lot. Okay, let's see a little example of this. Very quickly, I will show you the... Okay. So, this is a simulation of an embedding on a chimera graph. So I took the chimera graph from DNX, this D-Wave Network X is part of the Wave Ocean SDK, and with this command you can retrieve the graph representing the chimera graph. And now I choose my simulated dynamic sampler, and I decide to implement this. I implement this graph with this command, this graph, into my sampler, SA, and I embed, with embedding composite, I embed the sampler, yes, here, and I'm asking to the sampler to solve my problem using this graph, okay? And I want back the embedding because I want to see it. If you look at what we have here, we have a lot of qubits that are representing one single qubit. Okay, so for Q0 we need 2 qubits, Q1 we need 1, 2, 3, 4, 5 qubits. Of course, big chain of qubits are not always a good thing. Okay, because yes, it's working like a procedure, but you have to tune them because a lot of times we have broken chains. With a broken chain, we mean that the chain of qubits, for example, this chain of qubits has some discordant values in it. Okay, so we notice that no, this is 0, this is 0, this is 0, this is 1, this is 0, and it's not good because it's ruining our problem. Okay, So big chain of qubits are not a good thing because every qubit has to act as one. But it is possible to do that in this way. So counting the logical qubits, the physical qubits, not logical in this way, that I need to express my problem on the chimera graph, it says 54. Okay, so 20 qubit, 20 logical qubits. This is physical qubits. Okay. So 20 logical qubits are 54 physical qubits on the last model of the wave. Okay, and looking at the same thing on Pegasus, okay, we can say that Pegasus is much better. You can see it because with implementing our 20 qubits problem, because Pegasus has a lot more connections respect to the previous model. In fact, you can see it that the longest chain is 3. That is different from the chimera example that was more than 5. And yes, in fact, we only need 31 qubits on the Pegasus graph to solve our problem. Okay? Perfect. Okay. Now I will show you another little example. But maybe, yes, very quickly. Okay, do you know the n-queens puzzle? You ever heard about it? Is a generalization of the better known 8-queens puzzle. The 8-queen puzzle is a puzzle that you can play on your own with a chessboard. And we have here a chessboard with 8 queens. You have to put these 8 queens on the chessboard in a way that none of them are in check by other queens. If somebody doesn't know how a queen can eat in a game of chess, a queen can always eat every other queens, in this case, every other pieces of the game when they are in the same row, in the same column, or in the same diagonal. Okay, so the game is to put these queens here in order that you cannot eat another queen. So if you look at this picture, none of them are in the same diagonal or in the same column or in the same row. Okay. The game is generalized, let's considering a chessboard of dimension n times n. So the n queens puzzle is to put n queens on a chessboard that is of dimension n times n. Okay? Perfect. So let's think about how to turn the problem into a cubo problem. We consider a vector of binary variables. We will take one for each square of the board where we are considering. Okay. Each binary variable is associated with a square. So the variable will be 1 if the square contains a queen, or 0 otherwise. So the first requirement that I want in my cubo problem is I want to have exactly n queens on the board, right? This is easy. So we know how to solve this kind of constraint. Is this one? this one leads us to this one, that leads us to this one, that leads us to this formulation. It's the same formulation that we see before. Okay, now we have the core, right? But now we have to add some constraint because it's not sufficient to put n queens into the chessboard. What are the constraints that we have to add? Think now, what are the constraints? So,
sorry, Daniele.
yes.
Did you define the number of qubits?
Yes, I defined the number of qubits that they are 1 for each square, so n times n.
So the condition on the number of qubits equals to 1 should be from 1 to n by n.
N squared, yes.
N squared, yes.
Yes, I roughly intended all the qubits with this n. Yes, you're right. Okay. So we want 1 queen for each row. Okay. We want exactly 1 queen for each column, and we want not exactly 1 queen for each diagonal, but at most 1 queen for each diagonal in both directions. Okay, seems like an L, because we have to realize we have to add some qubit for this inequality constraint. We have to add this constraint here for each row, and we have to add this constraint here for each column. Okay, is it possible to do it with the things that I tell you before? But there is no, but it is not this. It's not necessary here. I will see right now. So let's consider the problem from another point of view. So instead of mathematically calculating all the constraints, let's do this. So consider the matrix of the quadratic contribution of the cubo problems. Okay. This matrix has elements all the possible pairs of squares in the chessboard that are n to the 4. Okay. N square. We have n square possible n square possible squares, so possible elements in the chessboard, and the matrix that consider the couples of squares is dimension n to the 4. So to implement our constraint, we do the following. We analyze the matrix of the quadratic contribution, and for each pair that is forbidden, we increase the value of its weight. Simply. So the weight, by definition, is activated only if both qubits or square are in state 1, or both hosts are queen. Okay, so the idea is this one. I have this chess here. I have all the possible combination of couples of these elements here. So I can say that this element here cannot host a queen if there is any other element in the in his row, in this case, that has a queen. So I can add a penalty quantity to all the couples that are in this row. Okay? All the couples in this row will be penalized. Same thing for the columns, same thing for the diagonals. How can I do that? For example, I can define a function in this way. That is a function that returns, that calculates a linearized vector containing all the possible pairs of squares in the board. For in this example, for the row part. So once a specific row has been chosen, vector will have the value 1 if the pyro squares belong to the same row, 0 otherwise. Okay? So now I can start building my penalty matrix. What I'm doing here. Okay, I have this matrix here that has these dimensions. So I will look at every row in the chessboard. Okay, I obtain the vector of the elements in the same row, and for all the couples in this vector, Li, Rj are the elements of this vector that I've calculated. I will add a weight W that will be activated only if the two elements chosen on this vector are both 1. So for making an example on a restricted chessboard of 4 elements, I see that R equal row 0, 4, so row 0 and dimension 4 is this matrix here. Okay, this is the first row. Linearized is this one. Okay, so when I apply it to my matrix, I will obtain, look at this big matrix here that is related to the 4, 4 because it's 16 by 16. Look at this. Yes, look at this matrix here. We can see here that the first element and the second element are in the same row. The first and the third are in the same row. The first and the fourth are in the same row. The first and the fifth element, that is this one, are not in the same row. Okay, are not in the same row. So there is no need to add a constant here for now. Did you understand the logic? In this way, I am penalizing the rows. Also, if you go down, you see that it's the same thing for the other elements. Perfect. When I ask for the second row, I will obtain this, and I will continue to adding my penalty on the right couples. The column thing is the same thing. This is the matrix, and this is the linearized vector of this matrix. Using this same function, using the columns instead of rows, I will see that now, for effect of this kind of calculation, now the element 0 is penalized, is from respect to the elements of the same row, but it's also penalized respect to the element of the same column that are these, and these. Okay, so I penalize it, starting from, I penalize this couple, this couple, this couple, this couple, this couple, and this couple here. Okay, and I do it for every couple on the matrix.
I suppose you ignore the diagonal because it's trivial, right? If it's occupied, it's you don't consider it.
But I don't know, because I consider it only for completion, because I wrote this code in 15 minutes, so I've considered it, I admit. But why it's trivial? Because you're saying that it's trivial, but I don't know if we can avoid to put the penalization also in the diagonal part. So, for example, this is the diagonal part of the program, and let's see. Okay, so if you see here, when I apply the first diagonal, I also penalizing this couple here that was not penalized before. Okay. Okay, so I have to think about this, your formation. Okay, but
can I ask also,
Yes.
Just to see if I follow what is the procedure. So you're trying to fill in a matrix of penalization, and on the matrix, the 4x4 matrix on the left, is the example of the penalizations for a particular square in the checkerboard.
Yes.
So, and then you flatten that, and then you add all of these penalizations, the row penalization, the column penalization, and the diagonal penalization, and you flatten those for each one of the places in the checkerboard, correct?
Yes. Yes, correct.
Okay. Okay,
yes,
thanks.
Exactly. And I put it into the same matrix that has dimensions n square n, n square n, n dot n, n dot n. Okay. Okay, so at the end of this process, I have my code that I show you. Here. Very quickly. Okay, I want to show you some other things, so I will give you directly the solution of this exercise because it's trivial. Let me open a file. Okay, of course, the shape is n star n here. Okay. Is the correct shape. And here we have only to put our constraint for the number of queens. Okay. And our B matrix, that is our penalization matrix. Okay. So let's see it. Let's try with a real chessboard. So here I'm filling the penalty matrix. Okay. And this is the solution. You can see it's a correct solution. There are no queens that are one in check of the others. It can be because I say that these are not hard concepts, but if you do, the fact is that with a cubo problem like this, if you create a good cubo problem, the solver will always perform good. Okay, it's very, very related. Okay, so let's give me only 10 minutes now to show you some particular advanced annealing techniques. I will still maybe 5 minutes of break, but I will give you back later, because then, Riccardo, we will show you some other application of the wave. Okay, so let me show you very quickly. See, sorry?
Sorry, Daniele. One question.
Yes.
Is there, I suspect that there is more than one solution in terms of placement.
Yes.
Can you, can this method actually reach the various solutions? Is there a randomizing factor or probabilistic component that makes other solution attainable?
I think that if you run different times the same problem, you will obtain a different solution. Yes, because it's depending on different factor. And don't know for the simulated annealing, maybe it's the randomized part of the thermal energy that can lead you to some other global minimum that is the same, that has the same depth of the other global minimum. We have, yes, we have a different solution with different minimum that are equivalent. For the quantum annealing is the same, but yes, I think it depends on the, I think that if you run, let's try, if you run this problem different times, you will maybe obtain different solution. In this case, it's the same, I think. Try again. I don't know. In principle, it's possible.
Yeah, that's what I suspected. That running it several times in a row, replicating just the last cell or the one before the last would give the same solution. So the randomizing aspect is probably elsewhere. Maybe not in the solver, maybe in the solver. That was my question, really, but it's okay. Okay, thanks.
I don't know, maybe the randomized part is in the solver, because you can obtain different solution of the same problem with the same inputs. So I'm thinking about the way that simulated annealing does to, let's see, I think with 10,000 reads, it's taking a lot.
You're going to exceed your 1 minute.
No, this time is simulated annealing. So I don't see. Is this different?
No, it's the same.
It's the same? Okay. I don't know. But I know that this is possible to obtain also other solutions.
Okay, thank you.
You're welcome. Okay, so now very quickly, this part here. Oh, okay. So this is my first work with the D-wave quantum annealer. We try to solve something that is nearly impossible to solve with an annealer. In particular, we tried to solve a problem with real variables. It was not so useful at a production level, but it was very useful at a research level to show how the quantum annealer can solve a problem with real variables using advanced techniques. Okay, so a real problem with real variables is really bad for annealing techniques, because the landscape of a real variables QUBO is something like that. Okay, it's an L of, because we have, the problem is here. We can always express a number in its binary form. Okay, but in a binary basis. But the exponents here, okay, the part in front of the qubit is is in different scales. This is a problem for annealing. Okay, if you have parts of your algorithm that have coefficient of order 10, another part coefficient of order 100, etc. Okay. The fact is that the annealing will make a lot of, it will be very hard to solve by a quantum annealer or a simulated annealing. For a simulated annealing, is impossible. We will see here that quantum annealing can do something when simulated annealing can do nothing in this case here. Okay, so we tried to solve a linear system. I will go quickly in this part, only for show you something. Okay, so I want to solve this linear system with the wave. This is the matrix. This is the solution. This is the solution, and this is the this is the x that we are trying to find, and this is the solution. Okay, so we know the matrix and we know the solution. We have to find these three numbers here using an expression like that. Okay, using x, y, xi like that. I tried to use a simple annealing to solve the problem, and and also using 100,000 of cycles of annealing cycles and 100 tests, I never found the real value. Okay, but I was expecting it because it's a mess for this kind of problem, this binary representation of numbers. Okay, I obtained something that is really near to this one, really near to the real solution, but not the real solution, not the global optimum. How to obtain the global optimum? Using some refinement of solution. One can be the reverse annealing. What is reverse annealing? Is a feature from the used by the way PDF or a part of official course note? No, it's a part of official course note, and it is on the PDF that I'm using. It's at the end. Okay. This PDF, what PDF are we talking about in the presentation, right? This PDF here, this work here, you can Google the name and you can find it on archive. Okay, so what is reverse annealing? Two words of reverse annealing. Reverse annealing is an annealing with a starting point. Okay, so instead of starting from, you remember that for annealing you start from an Hamiltonian was, the ground state, and then you transform the Hamiltonian in the final Hamiltonian that you want to solve. Okay, so reverse annealing instead is annealing that starts from your Hamiltonian, but in a point that you know that is a minimum, a local minimum, and search for better minima in the neighborhood of this starting point. Okay, so the transverse field, that is the field, the magnetic field that regulates the annealing, increase to a value chosen by the user, that is the reverse of this. If for an equivalence with water, of course, for example, we can think that the reversal distance is the maximum level of water, in this case, that you want to use to find the new minimum. We will see that if you use a reversal distance too low, you will not find new minima. If you use a reversal distance that is too high, you will go very far, and maybe you can fall in a minima that is not a better minima than the one that you have. Okay. Using this white paper published by D-Wave that explain about the local refinement of solution with the reverse annealing, we know that there is a particular value of reversal distance, this value here between 0.7 and 0.8, where the probability to find a new global minimum is maximized. So let's try to use this new feature to solve our problem. What I did was to realize an algorithm that do the forward annealing. Now we are calling forward annealing because now we are talking also about the reverse annealing. So the normal annealing is the forward annealing. We find a local minimum with the forward annealing. So then we use this local minimum as a starting point for the reverse annealing, and we obtain a new point. This is a new minimum. So we ask, is the new minimum better than the old minimum? If no, we make another cycle of reverse annealing. When is a yes, I replace the old minimum with the new minimum found, And maybe I want to have another cycle of reverse annealing until we find the global minimum or we reach the maximum iteration that we want to do. This new algorithm, I can say I was able to solve the problem or to find the global minimum over 100 attempts 18 times. Is not too much, but it's 18 times bigger, so no, infinite times bigger than the 0% that I had with normal forward annealing. So normal forward annealing never found the global minimum. Forward annealing with refining or using reverse annealing, a cycle based on reverse annealing, I found the global minimum 18 times. So another thing that I can do is to introduce the pause. You can see the pause between the backward annealing and the forward annealing, because the reverse annealing has this phase. You choose the starting point, you increment the area of searching, and when the area of searching is determined, you start with forward annealing in order to fall into another minima. A pause in the middle of this sequence means that you are better searching this area. Okay, so physically you stop the annealing process for a tot of microseconds, and then you will resume the process after this time that you've decided. But pay attention, because pause cannot be too long for different reasons, two mainly. It will increase the computational time of each annealing cycle. I assure you that can be very high. You will not do stuff like this with 1 minute. And if it's too long, it may also risk to increase the search radius more than desired, and we can go everywhere, literally. In fact, I found there is a correlation between pause and search radius, between force and between pause also and the Hamming distance between two different solutions. So if the pause is long, the Hamming distance between two consecutive solutions obtained by the wave is bigger. So it means that pause is raising the search radius. And this is not good, because if I fixed a certain search radius for my backward annealing, I want to use this. And I don't want to go over, because I'm afraid that I can find some other minimum that are worse than the one that I have. Okay. With this pause, I realize a new algorithm, that is this one, starting with forward annealing and going with and retrieving a initial point of minimum, that is x start, this is x0, it's posed with x start. Okay, start is my first minimum. Now I have also the value of pause equal to 0. So, like before, I start the reverse annealing with pause this time, pause, but pause is 0 right now. So it's a pure reverse annealing. I obtained a new minimum point, and then I ask if this new minimum point is better than the old minimum point. If yes, okay, I can continue with my reverse annealing technique. If no, this time I will add a DT, a little time step, to my pause total time. Okay, so I will pause my reverse annealing only on a very short time that will increase every time I don't find a new, better solution. Right? So,
question?
Yes?
I'm a little confused about this time you're talking about. This is obviously not clock time, world time, it's internal time, but what time is this?
QPU time. This is QPU time. This is the time that is used only about only from the part of the QPU. Okay, is the effective QPU time that you're using for solve your problem. This is a part, of course, of the total time that you use to call a D-Wave to solve a problem, because you have to take into account also downloading, uploading time, preparation of the machine time, and also other times that I hope they will be zero soon enough. But this is, yes, a sort of wall time, but only for the QPU. Okay.
Okay. So sorry. So it's a time that has to do with the quantum state, basically. So we're talking about picoseconds, or
yes. We're talking about microseconds. Yes.
Or even smaller, maybe. Okay.
No. Okay. We are precisely talking about microseconds. The order of magnitude is microseconds. Yes.
Yeah. I had said picoseconds.
You said pico.
No. So it's 1 million.
No. It's sort of microseconds. Yeah. Because a one annealing time, one annealing cycles has 1 microsecond. Need 1 microsecond to be done. Okay.
And the maybe at the end, let you go on, but at the end, it'd be very nice to recap what the forward annealing consists in, quadratic optimization solving with the constraints, and what the reverse annealing with the reversed distance is, and how they actually interact, because we saw the mechanics of how you present the computation and the calculations, but the general sort of framework or logic of doing forward and then reverse, and finding every time, as you just show now, a local optimum. I think for me it needs reinforcement.
Yes, I know. Now this final part is only to show you some advanced techniques. So the first part was the important part that I show you, because it is the part that you really need to use a quantum annealer. This part is only a bonus, to take it like in this way. And I'm showing you that exists the possibility to use a set of functions that are really important, and then that can be used only with the wave. Okay, only not with a simulated annealing. This Friday you will see something more advanced with quantum machine learning on the wave. And maybe next we will organize maybe another seminar or something to explain better this, because only with this topic we can talk about it for years, not for days.
Thank you. And how do you determine the reverse distance? Is it grid search, like for normal hyperparameters?
Sorry, can you repeat? Is it
to find the optimal reverse distance for reverse annealing? Did you use some sort of a pattern search or grid search or something?
I used this paper here. They said in this paper that these distances substantially, if I remember correctly, because it was 3 years ago, but if I remember correctly, for almost every problem, this is a good reversal distance. So if you put your reversal distance between 0.7 and 0.8, is always a good choice. I use this, I don't see it deeply, but this worked, so I used this. So for concluding our speech here, okay, this is the result of the last version of the algorithm. Using also pausing, I was able to solve the problem 76 times over 100. Okay, it's a lot, because if you think about the fact that only with forward annealing, we found the global solution 0 times. Using pure reverse annealing, we found the optimal solution 18 times. And this was median average, of course. And using this algorithm here, so reverse annealing with pause, we increase a lot the probability of finding a new global solution. And then we found the optimal solution 76 times. Okay, so this is only a preview. If you're interested to go deeper in these topics, I suggest you to go to the D-Wave website. They have a lot of examples. Now maybe you can see it with more consciousness, with more knowledge, and you can enjoy it better. Okay, so is there any question?
I have one, but I'll let somebody else speak first.
Thank you, Sigi.
Okay.
I think that you're the only one that is survived right now.
Sorry, I'll be very succinct. I suppose the system you consider is always adiabatic, right? It's isolated.
Yes.
And so when you pause the computation, normally the quantum state of your qubits shouldn't change, obviously. I mean, if it does change, there's a big problem. So exactly, what's the physical meaning of pausing the computation if, meanwhile, nothing is supposed to happen to the quantum states of the bits?
It's a good question. I don't know precisely because I am a mathematician. I use this kind of computers. I don't know how to build one, but if I remember correctly, they can transform the Hamiltonians using a particular magnetic field. This is a transfer field, if I don't remember wrong. And maybe this time I think that they will stop the increasing of the magnetic field, but don't trust me so much because really I don't know this part of the quantum computing. So what does the pause? Why it is useful?
So they're perturbing. They're actually perturbing the system.
Yes.
In some way. Okay, it's a perturbation. Okay.
Yes. The pause, you can see it as something that say to the solver to search better in the area where it is. Okay, so like an example, when I change the Hamiltonian and I change its shape, if the quantum annealer was perfect, in every single instant, I have to be in the ground state. Okay, so it says the adiabatic theorem. But it is not real in reality. Maybe when sometimes I can be in other than ground state, and this is why I not always obtain the global minima. Okay. So with the pause, I'm saying, okay, let's freeze this shape of the function that you obtained in this particular moment of the annealing. Let's freeze it for 1, 2, 3, 10 microseconds. And then let's see if you can shaping it better in this pausing time to obtain to stay in the real ground state. I intended it in this way. So speaking of other, this is Breck. We return at 4 with Riccardo Mengoni, that will show you some advanced usage of D-Wave, quantum annealer, and we have a 10-minute break, but I'm here. So if you don't want to break, you can ask me something, or we can say that we are done for this part of the lesson.
Yep. To continue the conversation about the effect of the pause, somebody else asked the same question I did.
Yes.
And I think the fact you mentioned the magnetic field being applied more or less time as a function of the pause length. Mm-hmm. For me, classically thinking, because I'm a macroscopic object myself, so I think classically. Classically thinking in physics, I would think that it looks like they're trying to perturb the system from the ground state of the quantum bits in a way that is very reminiscent. It makes me think of the way we deal with diffusion of atomic diffusion, where you have a potential well, a trough, potential valley, and on the other side of the small ridge, there's another deeper valley, and you want to reach the deeper valley to be more stable and to find the better optimal solution. And the perturbation of the atom is called the uphill diffusion process, where normally atoms diffuse downhill all the time, so they choose the steepest slope in terms of energy. But if you perturb them, they can jump over that small hill. It looks like tunneling. It's not tunneling because it's macroscopic, or I mean, it's not quantum. But it looks like they're trying to do this by lengthening the pause. They're actually perturbing the system each time a little bit more. So classically, the analogy would be uphill diffusion of atoms, so that they can find something else behind the hill, something better.
Yes, like simulated annealing, you're saying.
Exactly.
Yes, maybe. This is not this is a good tip. Good point. So real life application of D-Wave, yes, something. The fact is that D-Wave is a very good machine. Is good to use. Is it's also funny because it's I like to express problem for D-Wave, and so for now we have some real life application. For example, the Volkswagen is working with D-Wave for traffic optimization. Airbus is working with D-Wave for optimization of road control. And Telecom Italia was working with D-Wave for something related to antenna placement or something like that. We have developed 2 or 3 applications. One is the most recent one was for the optimization for the Lega Calcio in Italy, and we optimized the Series C tournament. But right now the fact is that we need a D-Wave in our facility, because right now it's very uncomfortable, the fact that you can use a D-Wave only if you connect the D-Wave during your computation. For example, if I have a supercomputer, I want to use a supercomputer, I did not run my program on my laptop, and then at a certain point of the code, I upload my data to the supercomputer, I process it, and then I download it. Okay, no, I go directly on the supercomputer at the beginning. I install the program on the supercomputer, and then I use it. Okay. This is not true with D-Wave right now, so it's a little bit underused for reason like this. But I'm very sure that it's a very promising technology, and it will be used when this kind of problem will be done. From 18% it's a lot, but if possible in the future solve it 100% of times, yes, maybe. Something that I didn't do is to try this algorithm with the new D-Wave. Maybe can be very improved, because this work was made using the last annealer, the last model that was a model with 2000 qubits, Chimera, with Chimera graph. Pegasus is real better. Reference about posing. Thank you. Thanks, Luca. Okay. So that's all, folks. Oh, how many euros do you need to acquire for a... No, not so much, not so much. 15 million, 15 millions can be enough. No, it's the price, the commercial price of the D-Wave is 15 millions. Right now, I personally think it's a little bit early to buy one, but if you consider that Marconi 100, Marconi 100, that is our 15, sorry for my pronunciation. And if you consider that Marconi 100, that is our supercomputer, and it is the 9th most powerful supercomputer in the world, it was costed 30 millions, so double. I think that. Okay, but one of these days, we will have also a quantum computer. So I know Mare Nostrum. Of course I know it. Okay, so that's all, folks. This was my last lesson. I will be here, of course, also during the tomorrow and the day after tomorrow. But I said all I want to say. Thanks a lot for your attention. I leave you with Riccardo Mengoni, our rockstar, that will explain you some advanced application of D-Wave. Thanks a lot and enjoy the rest of the school. Bye-bye.
Thank you, Daniele. So I think we can wait another couple of minutes. So we're gonna start at 4 o'clock. Okay, so let's start. It's 4 o'clock. Can you see my slide?
Yes.
Okay. Okay. Perfect. So now in this last hour, we're going to see some Cubo formulation of problems that could be useful, maybe also for you. So we're going to address some NP hard problems, and we're going to see what does it mean. And we're going to formulate them in a way that allow the treatment with the D-wave, for example, or with simulated annealing. Okay, so this is going to be the content. So we're going to briefly review what we have seen today. I'm going to discuss what are NPR problems, and especially I'm going to focus on NPR problems that are useful in machine learning, like unsupervised or supervised machine learning. Okay. Okay, a brief recap of everything. In quantum annealing, or in annealer like the one by the D-wave, the process, so the annealing algorithm can be divided into, can be expressed by two Hamiltonians. So two, the Hamiltonian which describes how the system evolves in time. Okay, so there is the initial Hamiltonian, so the part, the initial way, so the annealer, how the annealer behaves at the beginning. So it's something like this, and the role of this Hamiltonian is to put everything in superposition. And then the final Hamiltonian, that is the Kubo problem that you want to associate it to the Kubo problem that you want to solve. Okay, and then the annealing process works like this. So it's a combination, okay, of these two Hamiltonian. At first, so they are modulated by these two terms A and B. At first, as you can see, the dominant term is the initial Hamiltonian, so which is also called the tunneling Hamiltonian, which tends to put everything in superposition. And then gradually A is decreased, and it's instead increased B, which is associated to the problem Hamiltonian. So there was also this question about the pose, and usually what you do is you pose around this 0.4. So when there is the intersection between the two, the pose allows you to, let's say, search better, let's say, in your in the configuration space, because in this point you start to have your problem, so it's not 0B. So you start to the quantum annealer start to understand which is your problem, but still it's also high the tunneling Hamiltonian. So in this way, by posing, you can spread and try to tunnel and explore, give more time to explore basically the configuration space, and then you go on. And this is the forward annealing. Okay, in reverse annealing, as Daniele said, okay, you start from a configuration, then you go backward. So you start from the end, you go backward again, you stop at 0.4 again, and then you go in the forward direction again. Okay, so but the idea is to in pose or reverse is to stay for some time in this regime here, where both HI and H, so both the Hamiltonian of the tunneling Hamiltonian and the problem Hamiltonian have a comparable strength, so that you can explore better the solution space. Okay, so you've seen that we have the D-Wave, this Canadian company, and they produce quantum annealers using these superconducting circuits. and they have two devices. The latest one has 5,000 qubits, the previous one has 2,000. And they are arranged in different ways. So basically the 2,000 qubit has a chimera cell, so it's this kind of graph inside, so qubits are connected in this way. And the Pegasus cell is what the 5,000 qubit annealer has, so it's a more connected topology, so that's why it's give you better solution. And it also has much more qubits. What else? And you understood also that a QUBO problem, or equivalently an Ising problem, so that they are the same. And since these are, so the QUBO problem is something that can be written in this way. So you have linear terms and quadratic terms. You can put everything in a matrix. So the HIs give you the diagonal term, the JIJ give you the off-diagonal term. So basically you can interpret the QUBO as a weighted graph, okay? And what you do is, if you want to solve this on the D-wave, you apply this minor embedding. So you have to embed your logical formulation into the D-wave hardware. Okay, then now let's try to focus on what does it mean to solve an NPR problem with an annealing technique. So let me first briefly tell you, for those of you that don't have this background in computer science, let's say, so there is a part of computer science and mathematics that study exactly how complex is to how hard is to solve a particular problem. So, and that's complexity theory. Yeah. So, so they classify basically problems depending on how hard is to solve them. We can have problems that are called NP, which are efficiently solvable, okay, like multiplication, sorting, okay, for which exists an algorithm that runs in polynomial time. Then we have NP problems that are harder, they're like factorization of graph isomorphism. The problems that are hard, for which, let's say, NP stands for non-deterministic polynomial, but basically, you don't have a polynomial time, an algorithm that runs in an exact algorithm that runs in polynomial number of steps. Okay, but these algorithms, these problems are such that they are efficiently verifiable. The solution is efficiently verifiable, like for example, factorization. If I give you a number n really large, it's hard to find the prime numbers that multiply to give you n, but if I give you the two numbers, it's easy to check if they are a solution. Then we have NP complete problem that are the hardest problem of this NP kind, like traveling salesman problem, the n times n game of Sudoku, so something like that. And they are the hardest inside this class. Finally, what we're gonna see today is NP hard problems. So NP hard problems are problems that are at least as hard as the NP complete problems, and a lot of real world applications belong to the NP-hard class. Okay, so you can find a lot of optimization problem on graphs, on scheduling, but also some parts of many machine learning problems belong to, so let's say subroutines of machine learning problems belong to this class. That's what we're gonna see today. So let's try to formulate in QUBO terms some machine learning tasks that are NP hard. Okay. So let me first start with the unsupervised learning part. So probably most of you know what's unsupervised learning. But first of all, let me ask you, is it okay so far? Write in the chat, or if you have a question, ask with your microphone. Okay. Is it the first time that you see this kind of P and P classes? Probably for you, for those that have a more computer science background. Okay, yeah, of course. But yeah, okay, so, yeah, for me, for some of you, it's the first time. But okay, yeah, this is basically the idea. Yeah. Okay, so let's yeah. P equals NP. It's quite hard to prove, and probably not true also. It's okay. So, but basically, you know, there are different. I mean, problems are of different kinds. So depending on how hard it is to solve them. Okay. So unsupervised learning, I was saying, in unsupervised learning, you have an unlabeled dataset with, and your goal is to find patterns or structure in this dataset without the prior experience of the problem. So you don't have labels or anything. So the standard example in this unsupervised learning world is clustering, where you have some data points in the form of multidimensional vectors, and you have to assign labels. So like in this picture here. And so you have to group vectors, which means data, in such a way to minimize the distance between elements that belong to the same group and maximize the margin, so the distance between different classes. Okay, so one example is k-mean clustering. K-means clustering, basically you have your data set containing m vectors, okay, each one of dimension n. And the task of the algorithm is to partition this data set into k classes. So you can define each class as C1, C2, Ck, in order to minimize this function here. What does it mean? It means if you consider well, basically, I'm going to give you a cubo formulation, but Ising and cubo formulation is just the same, and D-wave accept both. Okay. What you do usually, so in cubo formulation, you have binary variables, which are 0 and 1, and in Ising problems, you have binary variables that are spin variables, which means are assume values -1 and +1. So it's just, so the form of the cube is the same. You just do a change of variable that may increase or decrease your global function that you want to optimize by a constant. So and additive constant are meaningless when you want to minimize something. Okay, so it's exactly the same. Okay, let's. Yeah, it's yeah, okay. So let's go on. Okay, you in this k-mean clustering, what you want to do is to minimize this distance, which means that you want to minimize, as we said before, the distance between the vectors that belong to one class with distance between all the vectors and the centroid. So like a mean vector, which represent like the central point of your class. Okay. So the way the algorithm works is the following. So at first you initialize. So this is your data set. In iteration 1, you randomly so you randomly assign a position to the 3 centroids. So, and this don't have to be good position, like in this case they are very clear, very close one another. And after every iteration, what you do, so what the algorithm does is to calculate every time the distance between the points and the centroids, and update the centroid. And after a few iterations, as you can see, the algorithm can group and cluster these 3 classes. Okay. So let me repeat again. So you have to first randomly select k centroid. So and you follow this iteration step. Yes. Okay. Yes, that's also true. You also have to select how many centroid you want. Okay. It's not. It's also that is not. Yeah, it's something that you have to decide from the beginning. So yeah, you decide how many clusters you need. So you select randomly your centroids, and then repeat these steps. So yes, you have an assignment step where each vector is assigned to a cluster, whose depending on the Euclidean distance between the vector and the centroid. Then you have an updating step where the new centroid is calculated depending on which vectors are associated to this cluster, and you repeat this after you repeat this process. However, the algorithm does not guarantee a convergence to a global optimum, but towards a local minimum. Moreover, as I was saying, the overall performance is largely affected by the initial choice of the centroid. Moreover, from a computational point of view, so from the point of view of complexity theory, finding the optimal solution for k-means clustering problem is NP-hard in the Euclidean space. Okay. So this is a good candidate, and what we want to do is let's try to formulate the clustering problem as a combinatorial optimization problem that we can address by annealing or simulated annealing or quantum annealing. Okay, but the aim here is to convert it to a QO problem. Okay. Okay, let's go. Let's see this one. So as you have seen today, this morning with Daniele. When you want to formulate a QO problem, you have to make a choice about what's the meaning of your binary variable. Okay. So in our case, again, since we have m feature vectors, we want to partition the data set into k clusters. And our binary variable, which I write as Zik, is defined in this way. So it is 1 if some vector, if the vector xi is associated with class ck, and 0 otherwise. Okay. So if my first vector is in class red, I will have zeta 1 red equal to 1, okay? And for the classes blue and yellow, I will have zeta 1 blue and zeta 1 yellow to be 0, okay, for example. Okay, and this is our first constraint, since the vector xi must be associated to a single class, of course, because you don't want a vector to belong to both the red class and both the yellow class. Okay, you want just one class. A smart way of mathematically ensuring this is to have that the sum of all the possible zeta associated with some vector to be 1. Okay. Let me think. Class Ci should be class Ck. No. Okay. Yeah. Sure. Here it's Ck. It's not Ci. It's Ck here. Yeah. K is for the classes. I is for the vectors. Yeah. Sure. This is Ck. Okay, then. Is this clear? I think also Daniele used this morning to ensure that there is only one class accepted for each vector. Okay. So is this clear? This relation here? Or if not, just say no, and I will. Okay, so let's go on. So the fact that we have defined our binary vectors in this way, our binary, our binary variable in this way, and the fact that we also have this condition, we can rephrase this condition in terms in cubo form already, so in terms of an objective function in this way. So basically what you do is, if you look at this equation on the right corner, you take the 1 and put it on the other side, and you square everything. And then since this should hold for every xi, you sum over all the i's. Okay. So what does it mean? It means that this function has minimum only when this condition is satisfied. Okay. If, for example, vector I, xi, is associated to two classes, this sum will give you 2 minus 1, that is 1, so it is not minimum. Okay, the minimum of this is 0. Okay, this is the first part, the hard constraint of the cubo. Then what we need is to also, so this was a structural constraint. Okay, so here we are saying I want in my clustering that each vector is associated to only one cluster. It's fair. Okay. The second part is the minimization. So the way we think is in the cost function, we want to penalize, which means we want to give a higher contribution to a situation that is bad. You mean when zeta ik is not to non-integers? I don't know. So in this case,
meaning any object of the cloud of objects would belong 40% to one cluster and maybe 60% to another one. And of course, local probability for the object can never be greater than 100%.
Okay, yeah, probably you can do something here in the cost function. I don't know. Maybe if you require
the cost function doesn't change. I mean, the constraint doesn't change. It's the same.
Or maybe if you put in the constraint a -2 instead -1, you allow 2 possibilities. Probably, I don't know. Or maybe you leave zeta I as integers, or you say you use zeta I as non-integers, but then
the objective function doesn't change. It's exactly the same.
Okay.
So it's just that you allow zi uppercase to be between 0 and 1, not just 0 or 1.
Okay. But okay, this is possible, but then you need more qubits. I mean, the variable should be binary. So in order to do what you want, you need, as Daniele said in the last part, you need to represent something that is real between 0 and 1, so using bits. So you need to write the zeta I in more like using the binary form. Okay, so you need more qubits.
Yes.
That's
Lucius,
probably.
Yes, Lucius pointed out that because there will correspond to logical qubits, it's going to be complicated, and that was the reason for my question. Yes.
Yeah. Of course. Yeah. Then okay, let's go on. So the penalty part, as I was saying, is this one. So okay, here let me say the distance between vectors is this dij. Okay. If in order to define a cluster, we want to group together vectors that are close. Okay, so it is necessary to add this penalty term. This penalty term is higher, so gives a higher contribution to the function that you want to minimize when zeta I and zeta j, so when these two vectors belong to the same class, but they are very distant. Okay. And this all you need to perform the clustering. Okay. The final QUBO associated with the clustering program is therefore the first term, modulated by some strength, plus this penalty term. Okay. I don't know if this penalty part is clear. If not, ask questions.
Yes, but you're introducing a bias in your clustering, which is okay. I mean, just a comment, which is that you are putting emphasis on local proximity or similarity on a local scale, on a local, very locally, not long distance, only short distance. I mean, long distance will be disadvantaged with respect.
Yes.
But I mean, the resulting clustering will be more precise on a shorter scale than on a larger scale. It'll be more precise. That's what I'm saying. This penalty function is biased in a way, but it's a well-known problem in machine learning.
Okay, that's not very clear to me, but it's biased.
It's just you put a higher emphasis. You sort of favor a representation of local similarity over the accuracy of representation of longer distance dissimilarity. Longer distance means dissimilarity, less similar. and it'll be less precise at a longer distance than it will be at a shorter distance. That's something you can observe.
Well, again, is not very clear to me the meaning of this. But okay, okay. Here, what I'm doing just yeah, I'm assuming that vectors that are close. I want to group together vectors that are close. Okay, so okay, and vectors that are far. I don't want to group them together. Okay, so that's what this penalty term does. Okay, it's quite simple, but then probably yeah, there are some problems concerning this assumption. Probably. Okay. However, we have this parameter lambda that modulates the strength of the first term, because this is an hard constraint that we want. Basically, we want the first term to be much higher than the penalty term here, because this should be satisfied, absolutely satisfied, in order to have a meaningful solution. Okay, that's why lambda must be much higher than basically the largest contribution that you have here. Okay, so let's go on. Okay, then let's try. So this was about clustering. Let's see another approach to clustering, that is with the minimum spanning tree clustering. So what is minimum spanning tree? In minimum spanning tree, you have a graph. This problem, you have a graph which is weighted, and you want to find the tree. So the subgraph of this original graph, that is a tree, and that touches all the vertices and minimizes the sum over edge weights. Okay, like this one. And you can apply minimum spanning tree to clustering in this way. So of course you have your cloud of points, of vectors, and at first you consider the weighted graph G, which is a complete graph, so you connect all points together, and weight is given by the Euclidean distance between the vectors. Okay, then you apply the minimum spanning tree on this weighted complete graph, and you get something like this. Okay, then in order to perform something that is similar to the k-means clustering, let's say, what you have to do is just so if you want to obtain k clusters, you just remove from the minimum spanning tree k minus 1 edges. Okay, so for example here I remove k minus 1. So at first I sort the edges from longest to shortest, and then I remove the first k minus 1, like shown here. I remove this one and this other one. This way I find 3 clusters. So one question. So Q is required for k-means with quantum scales. Okay, for this case here, the number of qubits that you need at the end is this zeta ik, which are exactly, it's the number of vectors times the number of classes. So yeah, exactly. If I have 3 classes and 100 vectors, it's 300. Yeah. Okay. So I mean, I guess this is clear. And probably, I don't know, this may ask also the question that we had before. I don't know. So I know that this technique is is different from k-means clustering. First of all, because you don't have the initial choice of the random choice of the centroids, and there are probably some data set where this minimum spanning tree clustering works better than the k-means. For I don't remember exactly where, but when probably there is some boundary in the data set. So okay. However, the minimum spanning tree alone is actually is not very hard. There exists okay, let me go back. Okay, so the minimum spanning tree problem is so is not hard. It's the complexity is not MP, but if we add a delta degree constraint, which means that we don't allow vectors, nodes in the minimum spanning tree to have more than delta neighbors, then the problem becomes NP hard. Okay. So what we want to do is to formulate the delta degree minimum spanning tree problem on the as a cube, no, and see. So we're going to see how can we do this. Okay. Okay, there is one question multiplied by the NBR number of classes to which any object can belong to simultaneously. Well, okay, I think now for k-means is just so the number of qubits or logical qubits or number of variables is just all the zeta ik's that you have. So yeah, it's just the number of vectors times. Okay, for fuzzy clustering, I don't know. I mean, for me, for fuzzy clustering, you need yeah. For fuzzy clustering, probably if you need zeta I not to be if zeta I is not binary, but it's a real number, that you have to multiply this by the number of digits that you need to represent that real number in binary. So probably that's also. So for example, if I want to represent 5, I need 3 bits. Yeah, I think I need 3 bits for 5 now because it's 100, if I'm not wrong. Okay, so you also need so 5. I mean, so then normalize everything in fuzzy, maybe, no? Between 0 and 1. So 5, it's like having 20%. I don't know, 0.2. So you encode it into 3 bits. You need. That's what, if I understood correctly, the meaning of fuzzy thing. Okay. However, let's go on. So let's try to formalize this problem in cubo terms. This is a little bit more complicated than the previous one. Okay. First of all, the first part is I have to introduce my variables. So let's okay. First of all, let me say. First of all, I consider an ordering of the vertices inside my graph. Okay, and the ordering reflects the structure of the tree that I'm looking for. So the root will be indexed 1, then the children of the root are going to be 2, 3, or 4, and so this way, and the leaves that are far from the root are going to be n and minus 1 and so on. So that's what I mean by ordering of the vertices. Okay. So I want first of all to associate to each vertex an index, so a position in the tree. Okay. So I can introduce my variable xvi, which is 1 if some vertex v is in position I. So for example, if vertex v1 is the root, then x v1 root will be 1, okay, and 0 otherwise. Okay, it's the position inside this ordering that I do on the graph. And I also introduce this other variable that is ypi, that is 1 if the vector p is the parent of the vertex in position I. So when you have a tree, you have, of course, parents and children. So it starts from the root, which is the parent of the first generation, and so on. Okay, it's like like the tree, family tree. Okay. Okay, you can also reason in this way. Since the root has no parent, of course, you know that yp1 must be 0 for every vertex. Moreover, since in a tree you can put in such a way that every root could be seen as the root, so you can pick the root randomly. And so we already know which is the root. We start by knowing which is the root. And so we already know that we already know which are the children of the root. So this means this one, okay? So we can safely restrict to the case where ypi I is greater than 3, okay? So, okay, let's start to introduce the constraint, okay? These first two constraints are the same that we have seen for the clustering problem. Basically tell you that there is the one-to-one correspondence between vertices and your ordering. So you cannot have vertices that are ordered with the same number or vice versa. Okay, there is a binary. Sorry, there is a bijection between your vertices of the graph and ordering of the graph. Okay, every graph has a order. Okay, as a particular label in the ordering. Okay, the second one, the second constraint is this one, which means that basically every vertex must have only one parent. So it's just this constraint. So it's only a it's not a bijection in this way, like here. No, it's just in one way, because parents can have multiple children. Okay, but a vertex has only one parent. So okay. Then we can add other constraint. So this constraint basically ensure that the graph is a tree. So what you're looking for is a tree. So for example, so it tells you that if vertex P is the parent of some vertex in position I, then the parent should be in a position that is smaller than the position of its children. Okay, so in this term exactly does that. So penalize the opposite. So penalize when the parent has a label in the ordering that is larger than the one of the children. Okay, so basically what I'm saying is that, for example, the root has 1 and the root cannot be 2, and a children of the root with the children of the root be in 1. Okay, so the ordering must be meaningful in the sense that must follow the generations in the tree. Okay. This other part ensures that when you select a children for a node that is a parent, these two should actually be connected in the original graph. But this is this term, of course, it does not give any contribution if the graph, if the original graph is complete. But we added this term just for completeness. Okay. Finally, okay, the Kubo looks like this. We also have these other two terms, the last two terms. So the last term is the actual minimization. So you have to minimize the sum of edge weights, where the weights are these W's. So the first three, the first four, first five terms we already seen are the ones that we've seen before. This is the minimization of the vertices of the edge weights. What about this term? This term is the one that realizes the delta degree constraint. So basically, we since we don't want vertices in the tree to have more than delta connections, delta number of connections, we add these delta -1 slack variables, which whose effect is to minimize this part. So basically, if by chance there is some vector, some vertex P that has more than delta neighbors in the tree, then this will the slack variables will activate, but one of them, I mean, only delta -1 of them will activate, but there's going to be one that is outside, left outside, that increase the value of this function. Okay. So basically here we only require delta -1 because we are only looking at children, no? Of course, every vertex has a parent. So the parent plus the children should be at most delta. Here, since we are just looking at the children, we know for sure that everybody has a parent except the root, but so that's why we put here delta -1. So because we are just looking at this children, okay, of a vector of vertex P. Again, like in the other case, these terms here are hard constrained, which means that if they're not satisfied, what you're looking for is not the minimum spanning tree, something different. Okay, so that's why the A term should be much higher than the B term, that is the minimization part. Okay, and so, or in other terms, you can put it in this way. Okay, for this particular problem, so A should be larger than B times the maximum weight that you have here. So are there questions concerning this part? This was basically probably more complex than the first one, but I mean, if you look, if you have time to look at it more with more calm, it will be pretty clear. Okay, can I go on, or are there questions?
I have one question.
Yeah.
I was wondering, so it depends on the choices of A and B. Maybe the problem doesn't have a minimum or have multiple local minimums. Well, I mean, this seems to be two parameters that define how good is the approximation of the optimization.
Yeah, I mean, in general, okay, for the problem to be, let's say, absolute, I mean, correct, you need to have A much larger than B. So it's like A equal, to infinity and B 1, okay? In theory. Because these are, the strength of this constraint must be much higher, are structural constraints somehow, okay? So they must be much higher than the minimization part, okay? So if you select, for example, and that's what actually happens on the D wave, because on the D wave, all the terms get mapped between -1 and 1. So at most, A becomes 1, for example, and B has to be as low as possible. So probably 0.01, I don't know, because then you go beyond the precision of the D wave, okay? So, of course, what you're solving on the D wave is not the mathematically correct formulation, but it's something approximate, of course, yeah. So probably this answered the question. But yeah, in general, so mathematically speaking, A must be much larger than B. So like, yeah. So this must be true in order to be sure. So at least you need this one in order not to mix. At least in order to be in this regime, in order so not to mix, let's say, energy levels. So if A is smaller, so is A over B is smaller than the max, then you may have a configuration where you prefer to not to satisfy, I don't know, maybe this constraint because you gain more by some term, activating some term here, okay? So that's something that you don't want to happen. Okay, that's why at least you have to set A and B greater than the maximum, A over B greater than the maximum weight, okay? Okay, can go on probably, and try to, so we have 10 more minutes, and supervised learning, the last part. So probably you know, but supervised learning, so it's a technique to, you have this time data set that is labeled, and you want to induce a classifier, and this classifier is a function that allocates a label, so you can classify vectors that have never been previously analyzed. No, it's the classical supervised learning techniques. Classification and regression are usually into this supervised learning ensemble. Two of them, so a method, let's say, that is very common, it's very used, is support vector machine, where it's a binary classifier. You have two classes and you want to find the best discriminating hyperplane that divides the two classes. So, of course, as you can see here, you have H1 that doesn't separate the two classes, H2 that does that, but H3 is better because maximizes the margin, okay? What happens if your data set is not linearly separable? What you usually do in support vector machine, that is an example of kernel methods, what you do is you map, let's say, your initial space into a higher dimensional space where linear separability applies, and you do that, let's say, by using this mapping, but actually you don't need to know the mapping. All you need to know is something that is called the kernel function, that is basically tells you how the scalar product behaves in this higher dimensional space. So graph at distance. So graph at distance could be used to define a kernel when your dataset is made up of graphs. So every point is a graph of some kind, and you want to discriminate two kinds of graphs, for example. And the distance between graph is the edit distance. The edit distance between graphs is defined as the minimum operations that you have to do in order to transform one graph into another one that is isomorphic to the first graph. Isomorphic means that, I mean, their topology is the same, okay? So you can use the graph edit distance, defined like this, as I said before, to define some kernel that you can use on support vector machine, for example. So the kernel is going to be some function of the graph edit distance between the two graphs, so the 2 points of your dataset. What does it mean, operation? Operations are like insertion of edges. You can insert edges, delete edges, insert vertices, or delete them. So we're gonna define a graph edit distance. What I want to do here is to calculate the graph edit distance, which is an NP-hard problem, the calculation of the edit distance, and I want to calculate it using the D-wave, and so I want to formulate the edit distance calculation as a QUBO problem. So how you do that? In the following way. So consider two graphs, G1 and G2, with the same number of nodes for simplicity. And we define a binary variable which associates vertices in the first graph to vertices in the second graph. So basically, XVI is 1, is vertex B in one graph, is mapped into vertex I in the other graph, and 0 otherwise. Okay? So this is a bijection. I mean, again, it's a bijective map between the vertices of the two nodes, of the two graphs, okay? So that's why we have these two constraints here. So basically, the first HA part tries all the possible mapping of the nodes of the two graphs, okay? But of course, one node should be mapped only into another node, not into multiple nodes, okay? That's why we need this constraint. Then there is the penalty term here, which penalize a bad mapping. What does it mean? It means that penalize the situation where some vertex I and vertex J in G1, which share an edge in G1, so they are connected in G1, and they are mapped. So I is mapped to U and J is mapped to V, and they are mapped to, so I and J are mapped to U of V, but U of V, which belong to the other graph, are not connected instead. So a bad mapping is when you map two nodes that share an edge with two nodes that do not have an edge in common. Okay, that's a bad mapping. Basically, and this is what this constraint here does. Okay, so you have these two terms because it's on both sides. Okay, you do it for J1 mapped into G2, but also vice versa. Has to be true. Okay, that's why you have these two terms. Okay, then in general, so the general form is this one again, where you have A and B to be again, they are the strength of these two. The first line here is the hard constraint, so A has to be much higher than B in theory. So, but you can prove that, like we've seen before, is this condition holds, basically you are okay. Okay, so you the solution that you find are correct. Okay, and I think okay, it's 5, and yeah, I'm right in time. Okay, you can, as Daniele said, okay, you can use this the D wave. You can add, you can access leap and try also the problem to solve problems that are proposed here using the D wave. You have access to, probably you've seen, to the advantage system. So you have 1 minute if you have the free account. The advantage system with 5,000 qubit, the way 2000 with 2000 qubit, but also you have hybrid approaches. So they're basically black boxes. So you don't know actually what the wave is doing. They say they split the problem and send it in parallel to the D wave, to simulated annealing, and to taboo search. That is another optimization technique. And then they get the best answer. So, so you don't know actually where your answer come from. Okay, from which of the 3 paths. Okay, but you can use this, and of course, since there are techniques that allow you to split problem, large QUBO problem, into first analyzing sub-QUBOs. So you split the QUBO into sub-QUBOs, and then you solve them independently, and then you put everything together. Okay, this is an hybrid technique that could also be helpful for solving real-world problems. Okay, and yeah, that's it. Other questions concerning this part? It was a little bit fast, but please, if you have questions, don't hesitate to write in the chat or use your microphone. Is it clear, more or less, this part? There's nobody left.
We killed them all, Riccardo.
Yeah.
I do have a question.
Yeah.
Does this mean that solving this type of machine learning problems depends on the number of qubits? Because the matrix, the connections resolve is the number of classes versus the number of data points.
Yeah.
And so that limits the amount of data points that I can use. Is that correct?
Yes. I mean, you have, for example, in this problem here, you have, I think you can solve graphs with, so the number of variables that you need is, if you have graphs of, with n nodes, is the number of logical variables that you need is n squared, okay? In the other problems, it was different. It was, as you said, for example, the number of elements times the number of classes. So of course, the number of you need in the optimal, in either world, you will need 1 qubit for every variable, okay? But then the wave, for example, doesn't have also the same connection as your QUBO problem. So you're going to need actually more qubit for the same logical variable XVI, for example. Okay, so yeah, basically with the D-Wave 5000, so you have 5000 qubit. I mean, you have 5000 qubit, and depending on how connected, how how connected is your cubo problem, the graph associated to your cubo problem. And so depending on the topology of your cubo problem, you're going to need more qubit if the problem is more connected, okay? If the cubo problem is sparse, you probably, you can also need just one qubit for each variable, okay? So, but as I was saying, there are techniques to split the cubo into subcubos. So you just focus on a smaller problem that you maybe can embed easily on the D wave, and then do it for all the sub-problems, and then put everything together at the end. So there are different techniques, okay? But of course, yeah, to have a one-to-one correspondence between qubits and logical variables, you need that, for example, the D-wave annealer and the cubo problem have either the same topology, share the same topology, or the wave has a completely connected topology, which is pretty hard to achieve physically. Okay, so there is this increase in the number of qubits, both because, yeah, basically because you need, because of the edges that you have in the cube. Yeah.
So just to follow up on this very same question, you just mentioned that if in the graph edit distance we have to consider n squared, where n is the number of nodes, but that's only for the hard constraints, because for the B group of constraints as it is shown here, you also have to consider the edges.
But the edges, in this, the nice thing about this formulation is that you only need one variable. So an edge here, in order to represent an edge, you don't need another variable. You use the same variables that you do for the node. So for example, here, when I have the...
Yes.
Okay, so
yes, thank you.
Of course, all these cubo formulations are not unique. So for example, the graph, the minimum spanning tree problem, this is it's a hard the problem has a huge formulation, but maybe it's not the best one. Maybe you can find a more compact formulation by and it's only in the initial choice of your binary variable. So what's the meaning of your binary variable? Then after, if you do it wisely, the problem may get easier. So probably here I can formulate everything, saying so that I have my binary variable that represent the mapping between edges, but then maybe it's harder to formulate the first constraint. I don't know. So they're not unique.
Yes. So, and I had a small question about the for the MST clustering, where actually it's common to various examples you showed. There was an inequality condition on A over B, so the sum of, for instance, for MST clustering, the sum of edges weight condition should always be satisfied. And I was wondering whether this A over B greater than the maximum value of the parameter W was actually strict. Strictly true as expressed. It seems to be very, very simple, and you just consider the maximum value of the parameter of all the variables W. I'm sorry, the set of variables W. Is that strictly true as an inequality condition, or is it, or does it have to be much greater than max? Or
okay, I think mathematically this is strictly true in order to have, let's say, to in order to separate configurations that are correct from the incorrect configurations. For incorrect correct configuration, I mean, for example, one where the graph that I found is not a tree. Okay, so this is mathematically what you need. Okay, but then physically, but also if you use not only quantum annealing but also simulated annealing. Okay, if these are too close, it means that solutions that are not correct are very close to those that are correct. And so in annealing term, it means that you can easily, the system can easily jump to those configurations. Okay, you need to separate well. You need to create a large gap between non-valid configuration and valid ones. Okay. So the larger A, the larger this gap between valid and non-valid configurations. The smaller A, the closer they get, and this relation, this inequality here, you have that when you are at the limit. Okay. After that, you start to mix incorrect configuration and correct ones. So the problem may end up in, I mean, the solver may end up in something that is not correct. Okay. Okay. Are you still here? Somebody else? Okay, I have a question about K-means clustering. But it's quantum representation does not solve the problem of its classical. Well, yeah, I mean, it's not exactly the K-means clustering. It's a quantum annealing. It's not exactly the K-means. It's a Cubo clustering using Cubo. It's not exactly the same thing. Yeah.
Yeah, Riccardo, sorry, can you hear me?
Yeah.
Just to clarify my question. Yeah, I meant the quantum annealing implementation, but still we have the same problem, right? That the convergence to the optimal, to the global minimum is not guaranteed, even in its quantum annealing implementation, right?
Yeah, I mean, I think the problem, so also in the annealing implementation, stays probably in the NP hard regime. So yeah, but usually with quantum annealing you don't have any, you're not guaranteed to reach any global minimum. The power of quantum annealing could be to employ a physical device to solve let's say a problem. I mean, yeah, of course. I mean, of course, with quantum annealing you cannot solve NP-hard problems efficiently, and you are not guaranteed to reach the minimum, because it's not adiabatic quantum computation where you're guaranteed. It's something that is not really adiabatic, because you have temperature that is higher than 0. You're not going slow in the adiabatic evolution. You're going pretty fast, as you've seen before. You go every annealing is 1 microsecond. So you're not absolutely guaranteed to reach a global minimum. Okay, but you can, the idea is that you can reach pretty fast a pretty good solution. That's the point of quantum annealing.
Thank you.
Okay, I hope this clarify.
Yes, sure.
Things. Are there other things?
And plus, you still have to choose the number of clusters to start with. So in quantum annealing, in the same way that we do in classical resolution. So
that's also true. Yeah,
that's a big issue.
Yeah, that's also true. You don't have it. I know. Yeah, in the minimum spanning tree implementation, the thing that you don't have is the random choice of the centroids, for example. So that might be good. I know that it might be good for some particular data sets. Yeah. Also in the quantum annealing implementation, the first one that we've seen, we don't have we don't have centroids. You just do depending on the distance. Yeah. Okay. Every mathematical problem can be transformed into a QO problem. Yeah. Let me say. So, okay, an intuition could be like at the end. So every function could be. So any problem could be turned into a say a binary problem. So, I mean, like classical computer do. At the end, everything is binary. Okay. So there is always a mapping of any problem into a QO problem. But then if you have, if you assume to have unlimited resources, okay? So if you assume to have, so you don't put a bound on your number of variables, okay? So everything could be turned into a binary function in general, okay? But if you have enough bits, okay, that's the idea.
I see. So the formalism, let's say, has enough complexity to capture any kind of problem as long as the size can be increased.
Yeah,
it's only quadratic, but I guess with the
you can turn also any. So okay, probably I also had this problem in the past where we analyzed problems that were in molecular unfolding. Probably you're gonna see this on Friday. So you can formulate problems into a UBO, so not QBO, so which means a higher order binary optimization, which means that you don't have only linear quadratic terms, but you also have cubic, quadratic, qubit, fourth order, fifth order, and so on. But then a term of any order can always be split into a sum of linear and quadratic terms.
Mm-hmm. And I guess we're talking about optimization problems or even more general kind of problems.
Yeah, any problem. For example, actually there is a result that Ising problem or QUBO problem are universal, which means that you can actually formulate any problem, even problem that are not optimization, as a QUBO problem. Okay, so For example, also factoring can be implemented as a optimization problem. It should be universal, so which means that you can formulate any problem in that term.
I see. Thank you.
No problem. Okay. Are there other questions? Okay, in annealer is not a universal quantum computer because okay, there are different kinds of universal quantum computers. Yesterday we have seen the gate model. Okay, the quantum annealer is something that is close to another form of universal quantum computation that is called adiabatic quantum computation. In adiabatic quantum computation, at first you need to be at 0 temperature, and then you need to that your process is adiabatic, which means slow. Okay. An annealer is an adiabatic quantum computer which is not at 0 temperature, so you have some thermal effects, and secondly, you're not slow in the process. You're not adiabatic. You go fast, because going slow means exceeding the coherence time of the qubit that they are using. Okay, so if you give up on adiabaticity and temperature, then no, okay, the quantum annealing is not equivalent to quantum Turing machine, or is not. There is quantum Turing machine that is equivalent to quantum gate model that is equivalent to adiabatic quantum computation. Quantum annealing, in some sense, is it's related to adiabatic quantum computation, but is not doesn't have the same. So it's like adiabatic quantum computation when you give up adiabaticity. So you also give up universality and the connection with the quantum Turing machine and quantum gate model. That's the meaning. Okay. But still, it could be. So the idea is that even though it's not universal, like gate model is universal, like we've seen yesterday, could be still useful for having solutions that are maybe beyond what a classical computer can do, because you can use, even if not in the adiabatic regime, you can still use quantum entanglement. And the idea is actually that. So the idea is that quantum annealing can beat simulated annealing, for example, when the landscape, the energy landscape, is such that there are a lot of minima that are separated by high barriers, which are very thin, which simulated annealing cannot usually escape, but quantum annealing could escape by tunneling. Okay, I think are there other questions? Yes, if not, see you tomorrow. And yeah, I don't know if Daniele is still here, so thanks, Daniele, for this morning. Yeah.
Thank you for this afternoon. So,
Yeah,
okay. Thank you, everybody. Last thing before we close, I will repeat tomorrow, but Cinega for the Italian students only for now. is offering also free computational time on the wave. You have to complete an Iskra project type C, and you can request some D-Wave time. Okay. So, see you tomorrow. Thanks a lot for your attention, and have a good night. Good evening. Bye-bye.
Bye. Thank you.